on. My name is Krupinski. I'm a mechanical engineer on this project.
My name is Owen McGarrity. I'm a mechanical engineer.
My name is Camitan. I'm an electrical engineer.
My name is Weisfeld. I'm also an electrical engineer.
My name is Schubert. I'm one of the CEs on this project.
My name is Zhang. I'm also a computer engineer, and our co-advisors are Wafi, Danesh, and Kerry. Team 13 came up with a project description that actually designs and manufactures a vehicle that can deliver food from the SUNY New Paltz campus, which will include members such as students, faculty, and staff. Our project will actually deliver our green reusable pass containers from point A to point B. The reason why we are doing this scope of work is because having a campus food delivery vehicle will enhance human convenience, especially for individuals with busy workdays, such as students who are studying for finals, or also professors that are lecturing classes. For Senior Design 1 and 2, our project will actually account for GPS and AI technologies that will control the movement of the vehicle, and also certain design aspects such as like different steering and different like hardware body parts that will be taken into consideration when accounting for terrain and also weather issues.
One of the first aspects of technology of our project is the use of GPS. The module we chose to use for this project is the Neo 6M GPS module, which recognizes the location of the vehicle using latitude and longitude. Our vehicle operates on what we call a nodal network. A path of nodes allows the vehicle to reach a destination. Once the vehicle reaches a node, the vehicle will respond and drive to the next node, eventually completing the path. These nodes will be recognized using latitude and longitude by the GPS module. Once the GPS module recognizes the correct latitude and longitude of a node, it will then drive to the next and complete the path. We hope for this task to be performed in 500 milliseconds. So once a vehicle reaches the node and the GPS module understands the latitude and longitude, in 500 milliseconds response, it will drive to the next. The second aspect of technology we use in this project is our obstacle recognition technology, our AI. To complete AI for this project, the Husky Lens K210 recognizes potential obstacles obstructing the travel of the vehicle on a path. The way this works is through a collection of images and photos uploaded to the ROM of the module to recognize these obstacles. In return, the vehicle recognizes these obstacles from a distance of 0.61 meters, approximately 2 feet, allowing for sufficient enough time to avoid these obstacles. The way that the Husky Lens K210 works is the use of the built-in machine learning technology to recognize. The third aspect of technology in this project is the battery management system. We're hoping that the vehicle will maintain charge for 3 hours before needing to charge again. In order to charge the vehicle, we're going to use a docking mechanism allowing for the vehicle to charge when idle. Our battery management system for the state of charge allows for the docking mechanism to stop sending current to the battery once the state of charge is 100%. We don't want to overcharge the battery, so we need some sort of battery management to make sure that our battery doesn't overcharge. Currently, there's no battery specification yet, as criteria is being tested using the bench power supply. We need to make sure the current being supplied to our motor is sufficient in order to select a proper battery for this project. Other core features for this project include the housing for the reuse pass container. This will stay locked until a 4-digit passkey is entered by the user who ordered the delivery. The logic for this is if the right passcode is entered, open the door. Else, do not open the door. We want to make sure that every delivery that our vehicle makes is secure and it goes to the right person, hence this security feature. Also, we want to include a fail-safe manual override of the system in case of a serious issue when performing a delivery. God forbid something were to happen, some sort of external force were to conflict with the delivery of the food, we can then control the vehicle ourselves to make sure that every delivery is fulfilled.
For the initial iteration of the prototype, we were exploring different options that we could have for the car, which included using 2 DC motors to power the back wheels for rear-wheel drive, and assuring that we had enough space for our breadboard, our servo, any other Bluetooth components that we might have. This is the initial shape that we had come up with. It'd have a 2-layer system where the bottom layer would contain all the electronics, the motor, any moving parts, which would then be isolated from any weather, so we'd have weather sealing. And then the top component would include the component that carries any of the packages, so any of the food packages, as well as the locking system for the door. So this is the dimensions that we had initially come up with, just based off of some of our first measurements and what parts we had initially planned to use. But further down the line, realizing some limitations to wheel diameter and other part limitations that we had, we decided to move on with a slightly different approach. So for the next prototype that we've been currently working on, we decided to use one motor that delivers power to an axle that will drive both of the back wheels. So we're still maintaining that rear wheel drive. We also changed our steering up slightly by using a rack and pinion to change direction. And we slightly increased the size to accommodate for our motor mount, as well as more space for any potential breadboards, and just kind of some other design changes that we had initially planned. We're going to rework our container that will have all the food containers inside, as well as our lock and keypad for that portion as well.
Okay, so this is our current benchtop setup. Right now we just have the rear motor set up with the wheels on the axle, and then an ESP32 with a H-bridge connected. And with the current setup, we can use this Bluetooth terminal to control the speed of the motor. So right now we just have set up at the bottom, you can't really see it, but it's 0 to 100%. And if you click them on the phone, first you gotta connect the Bluetooth. You can change the speed of the motor by clicking the buttons on the Bluetooth. And that's about all we have set up. Once we get the servos for the steering module, then we'll be able to control the steering through Bluetooth too.
All right, to say some things about the steering system now. Essentially, it's a fairly simple linkage. It involves a rack and pinion that's going to control the steering system. The rack, which is right here, will be attached to the pinion, and the pinion will be directly attached to the servo motor. And the servo motor, as it spins, it'll spin the pinion, which will in turn spin the rack. And as the rack slides, the wheels will slide, as you can kind of see here. This is the first version of it. There's a print going on right now which is going to include guide rails so that this rack will stay horizontal, so it's not sliding everywhere as it is now. But you can kind of get the gist. Yeah, we explored with some other designs, but we ended up with the rack and pinion, as we believe it's the most going to give the best and most direct correlation to the turning of the wheels. So this is what we came up with.
Our current plans for Senior Design 2 will include GPS implementation, AI implementation, and unison of all components. So for GPS implementation, we are going to map out the nodal networks using Map API, and also program the Neo 6M to read the current latitude and longitude. Whereas if a node is present, it will proceed to the next node, versus if a node is not present, it will stay at the node. For AI implementation, we are going to upload pictures to the Husky lens, and where it will utilize the photos to train the AI module to recognize objects and faces. Training of the module to recognize the obstacles will also be present, where it will avoid obstacles accordingly, during the path of the car. As for the unison of all components, software and hardware assemblies will allow for a fully functioning vehicle, whereas GPS and AI work together completely to task for the full delivery of the food.
Now we're on to the contributions for each of the groups. For the mechanical engineers, we were focused mainly on the CAD design of the thing and the steering. We just had to make sure the car was working and it could get from point A to point B. We also were in charge of assembling the parts of the vehicles and verifying that the CAD software and everything just kind of works together and works with the CE's and the EE's part. Now on to the EE's contributions. They were in charge of the PCB design and manufacturing the hardware. It's pretty much everything on the breadboard, getting the car to run electrically. And then they were also in charge of the implementation and assembly of the hardware of the system, and also the verification of the hardware, making sure it's receiving enough current and everything so the car goes. And now on to the computer engineers. They were designing the software of the vehicle, pretty much everything. Once we get to it, they'll get around to the AI. But they're also in charge of troubleshooting the code for the hardware. and also just implementing Bluetooth to make sure we can track the delivery and the vehicle itself so we don't lose it.